Okay. Hi, everyone. My name's Halley Goldberg, and today I'm going to talk about some joint work with Valentin Cabinets called Improved Learning from Kolmogorov Complexity. Okay, and just really briefly, what does the title mean? Well, we're going to show that if you have average case easiness of some problems of time-bounded Kolmogorov complexity, then you can do pack learning over arbitrary, efficiently sampleable distributions, and importantly, that learning doesn't require membership queries, so just learning from independent random examples. Okay, so to that end, we're going to be exploiting this kind of antagonism between pseudo-randomness and learning. So these important computational tasks are kind of at odds with each other. There's a sense in which one of them is possible if and only if the other's impossible. So I don't know if you're familiar with these magic eye puzzle game things, but I think it's kind of illustrating the phenomenon that I'm talking about. Because learning, on one hand, is all about being able to pick some structure out of a random-looking environment. Whereas pseudo-randomness really depends on any structure that is present remaining hidden. So that's kind of the source of the tension there. Okay, so a little bit more concretely, we can illustrate things with this generator that I'm calling G. So it's a potentially pseudo-random generator. F is a Boolean function. This is just a k-wise direct product of f. For simplicity, let's think of these xi's as uniformly distributed. Okay, well, we know from Yao that if we can break the generator, so if we can distinguish its outputs from uniformly random strings, then we get a predictor. So given some appropriate prefix of the generator, with probability a little better than half, we can predict the next bit of it. And already just in that statement of prediction, there's a little bit of learning going on implicitly, because what's really happening, we're given a number of labeled examples, xi along with f of x sub I, and then we're able to say something non-trivial about an unseen value of f. So we're learning something about f, and if you want to know f with better probability, you can apply some standard boosting techniques. Oh yeah, and by the way, just to mention, this kind of connection was discussed and given a bit of more formal treatment in a work of Adan. Okay, so I'll be a bit more specific about the type of learning that I'm talking about. It's Valiant's notion of probably approximately correct learning. So we want to learn some unknown target function f. It belongs to a concept class C. You could think, for example, of the set of functions computable by circuits of fixed polynomial size. We want to learn with respect to a distribution D. So we get examples x drawn according to D along with the values f of x. And then the goal of the learner is to produce with high probability a hypothesis H that agrees pretty well with f over D. There's a generalization called agnostic pack learning. So now f doesn't necessarily belong to C. And it's probably too much to hope that in polytime we could learn an arbitrary function f very well. But we can at least hope to do as well as the best function that does belong to C. So looking for H, that's almost optimally computing f with respect to C. There's also a version with membership queries. So now the learner at any point in the process can ask for any points of f that it wants. Okay, so for a little bit of background, there's this 2016 work of Carmesino, Impagliazzo, Cabinets, and Kolokolova, which is, again, exploiting the pseudo-randomness learning connection that I was talking about. Okay, so they show that if natural properties exist, in the sense of Rasparov and Rudich, then you can pack learn the same circuit class over the uniform distribution, and it'll require membership queries. Okay, so I just want to give you a little bit of intuition as to how they're applying the general framework and where the membership queries are coming from. Okay, so a natural first attempt, of course, would be to try to use a natural property to break the very simple generator G that I started with. So what's a natural property? Very roughly, it's an efficient way of distinguishing between strings of low circuit size and uniformly random strings. So to break the generator, we would want to show that its outputs are indeed truth tables of small circuits, or smaller than trivial at least. Okay, so we're learning over the uniform distribution. So the xi's are uniformly distributed. There's no hope of compressing them, so let's just hardwire them into our circuit. And intuitively, you might think that if the circuit size of F is small enough, and if we choose K to be large enough, then you might be able to get some circuit compression of those last K bits. But unfortunately, this intuition is kind of leading us astray, because if you actually go and try to implement a circuit with that sort of string as its truth table, just the amount of circuitry and multiplexers that would be required to take the appropriate xi and route it into the circuit computing F, well, it would completely overwhelm those k bits that you had to work with. Okay, so circuit size doesn't work, doesn't break the generator. It's like a too kind of cumbersome representation of that string. Okay, which is why the authors of CIKK turned to the slightly more complicated construction of Nissan and Vigdersen. So the point is that NW is much more economical in its use of the random seed Z. So it's kind of using and reusing Z to get a lot more stretch out of the generator. Right, you can think of NW as like a de-randomized version of G, or think of G as a really inefficient, design-free version of NW. Okay, but the nice thing now is that with so much more stretch, circuit size does break the generator. A natural property breaks NW, but it comes at a cost. Because now, in order to get a predictor, the values of F that you need to know are no longer independent. So the designs SI, they're not overlapping too much, but they are overlapping. So the learner is going, like once Z is fixed, the learner will have to ask for some very specific values of F, and hence membership queries. Okay, so very high level, but just to give you some idea. In the years since, there are some follow-up works. So the same authors in 2017 show that under a certain generalization of natural properties, you can also do agnostic pack learning. More recently, 2022, Benedict, Carmesino, Kolokolova, Ramya, and Sabin show that under standard natural properties, you can learn over arbitrary distributions that are sampleable by small circuits. Here, I'm not telling you anything new. I'm just remarking that the definition of a natural property is equivalent to average case easiness of the minimum circuit size problem. So we've already heard about this problem. It's the problem of deciding, given a string, whether it's the truth table of a small circuit. Right, so it's one of these kind of like central problems of meta-complexity, along with problems of time-bounded Kolmogorov complexity. I'll mention right now that Kolmogorov complexity is more flexible in the sense that short descriptions of strings don't have to take the form of circuits. They don't have to be interpreted as circuits. So in some settings, it's a little easier to work with, which brings me to our results. So we show that if there's a Kolmogorov complexity analog of a natural property, distinguishing strings of low KT complexity from uniformly random strings, then you can do agnostic pack learning over arbitrary, efficiently sampleable distributions, and the learning doesn't require membership queries. So just learning from random examples. So yeah, a bit more specific here. We kind of have two main results corresponding to two different versions of time-bounded Kolmogorov complexity. And I'll define those in the next couple of slides. But just for now, I'll mention that the difference between them is in the type of access that the learner gets to the distribution it's learning over. So in the top case, with k superscript t, all the learner needs to know is an upper bound on the size of the sampler for the distribution. And once it knows that, it can learn over any distribution of that complexity. On the other hand, for k capital T, a stronger form of access is needed, more like white box. The learner needs to know explicitly the code of the sampler in question. Okay, so as promised, some definitions. This one we've already seen. But yeah, k superscript T, it's sometimes called k poly. The T here in the superscript can take any value that you want. And then the question is, what's the minimum length of a description that could possibly be sent to a deterministic T time-bounded entity such that it could recover X? There's also a probabilistic version, which we use in our proofs, called PKT. So the difference here is that, think of the sender and receiver of descriptions as being in the presence of some shared randomness. And the descriptions, D, are allowed to depend on that randomness. So what's the minimum length, S, such that with high probability over randomness, there's some description of length S, which in the presence of the randomness yields X in time T. So it might bring to mind the definition of AM, just in the order of quantification, witnesses are allowed to depend on randomness. Okay, and then finally k capital T, sometimes called Allender's KT. So now we're minimizing both over description length and the time-bound T. And T gets explicitly added into the complexity of the string X. It's a more kind of local notion of the complexity of X. So we're only asking for one bit of X to be recovered at a time. We get random access to the description. And this is also getting a bit closer to circuit size. And in fact, they're known to be polynomially related. Okay, so now I claim that just from what we've already seen, it's already easy to learn over the uniform distribution from either of our versions of KT complexity. So again, our goal is to break G with Xi's uniformly distributed. So we're given some input with examples Xi followed by their labels Bi, which I'll denote X and B respectively for short. And we just want to be able to tell whether it's a random string or whether it's an output of the generator. In the case that we're looking at a random string, well, one thing we know is that with very high probability over uniformly random strings, they'll have nearly maximum KT complexity. So KT of X and B in that case will be something close to its length. On the other hand, if we're looking at an output of G, well, I want to show that we can get some KT compression of the string. So again, Xi's are uniformly random, no hope of compressing them. So let's just hard code them, their whole description. But then once we have those, if we want to get one of the BIs, all we have to do is look up the appropriate Xi, to which we now have random access, and apply a description of our circuit computing F. And if we choose our sample size, M, to be large enough, like say big enough polynomial in the circuit size of F, then we get the desired gap in KT complexity between the two cases, which are assumed heuristic for KT, will identify giving us a distinguisher, predictor, and so on. Okay, so I haven't mentioned how we do agnostic learning. And just for the sake of simplicity of this presentation, I'm not going to say much about that. But I'll just mention that there's a work of Kotari and Livni, which describes a problem not too different from the one I've described here, except in the latter case, instead of bi's being equal to f of xi's, they're just correlated with those values. And it turns out if you can solve that problem, which we can using similar ideas, then you can also do agnostic pack learning. Now, of course, I also haven't mentioned how we learn over other distributions. And I am going to spend a few slides talking about that next. But for now, let's just stop and think about why this argument doesn't work as is. Okay, so one issue is that with x's coming from some other distribution, no reason to think that kt of x will be close to its length anymore. That's not true in general. Okay, but even looking past that, even if we are able to get some difference in kt complexity between the two cases, which we can, in analogy with a natural property, we've only assumed easiness of kt over the uniform distribution. So now, with xi's coming from some other distribution, our inputs are coming from another distribution, and there's no reason to think our heuristic will work anymore at all. Okay, so at this point, we turn to a recent work of Hirahara and Nanashima. They give the same learning consequence that we get in the case of k-poly, but under the stronger assumption of being in the world called heuristica. So all of distributional NP being easy on average for deterministic polytime. And yeah, that's our starting point for the k-poly result. We want to try to apply some of the tools that they used in that work and keeping it working under the weaker assumption. Okay, so here's one of the key ingredients in the HN21 paper. It's a worst case approximation algorithm for k-poly, which you can show to exist under that stronger assumption. So for any string w, any time-bound t, you can come up with a value s that's like some sort of good estimate of kt of w. Now, if we had an algorithm like this, it would get us around the issue I just mentioned of our heuristic only working over the uniform distribution. So this is a worst-case algorithm, and it would work on any samples we get. Okay. Now, sadly, without the stronger assumption, we don't have such a nice algorithm. What we get instead. Oh, and by the way, the reason roughly is that we can't apply ideas from Berman, Fortno, and Pavan to de-randomize things. But okay, what we end up with is an algorithm that gives us a value s that's like sandwiched somewhere in between probabilistic k-poly of x and k-poly of x. And a priori, it doesn't look like this would be very helpful at all, because pkt and kt can be as far apart as you'd like. There's nothing tying them together in general. So how do we get around this issue? Well, here's another statement from HN21, which holds under the stronger assumption. Yeah, they use it for a different reason, to get around a different technical problem that I won't get into. But it says that for any efficiently sampleable distribution D, in the expectation over strings W sampled according to D, there's this kind of closeness between k-poly of x and time-unbounded k of x. So conceptually, this is really nice. It's saying that, at least in the expectation, over well-behaved distributions, kt of x is almost as nicely behaved as time-unbounded Kolmogorov complexity. And we actually use something similar in a number of different ways in the paper. Okay, I'll just mention that the proof of this statement is building on an earlier work of Antunes and Fortneau, 2009, and it follows from a source coding theorem for K-poly that you can prove under that assumption. Okay, but what's the point of this for us right now? Well, one thing we know about PKT is that it's always at most KT, and it's always at least K. So this statement also tells us that with high probability over strings coming from efficiently sampleable distributions, this kind of terrible looking algorithm from earlier actually would give us a good estimate of KT of X. With high probability, PKT and KT will be close together. Now, okay, you might guess that without the stronger assumption, we don't quite get that statement. But what we can show unconditionally is something similar that holds in the presence of some additional uniform randomness R. Okay, so looking back at our algorithm, it should be good enough as long as we have strings W and R coming from those distributions. So W from D efficiently sampleable, uniform R. All the samples we get are from an efficiently sampleable distribution, so that takes care of W. We just have to deal with this kind of annoying additional randomness R. Okay, but that turns out not to be such a problem because learners are allowed to be randomized entities. So they can sample as much uniform randomness as they want at the beginning of the process. And I don't have time to go into detail, but we just kind of incorporate that randomness into our distinguishers in a natural way. And the sort of gap that you can get between the uniform case and the generator case turns out to be preserved after that modification. Okay, so that's all I'll say about K-poly. For K capital T, I don't think I have time to say very much, but I just want to mention that in that setting, we don't have that worst case approximation algorithm that we have for K-poly. Okay, so we need something different. But one thing we know, which I actually already showed you, is that at least from this assumption, we can learn over the uniform distribution. So it then remains to reduce the case of learning over an arbitrary distribution to that of learning over the uniform distribution. And in order to do that, we use this idea from Impagliazzo and Luby, distributional inversion. Okay, and I won't go into detail, but essentially what we do is take a distributional inverter for the sampler of the distribution we want to learn over. And we apply it to all the samples we're given, and intuitively this kind of puts us back in the case of getting uniformly random samples. So I don't expect that to paint a complete picture of the argument, but I just want to mention it because it explains the need for white box access to the sampler. So in particular, the inverter needs to know the code of the circuit it's inverting. And I'm going to skip that. One open problem that immediately comes to mind is whether we can improve the conclusion of the K capital T result to that of the K poly one. And well, I don't know, but it is possible to show that if KT is easy in the worst case, then you can get the same conclusion. So this, I think, is just indicating that really the only missing piece of the puzzle is the worst to average reduction that we have for K-poly. Two final open problems. Ultimately, ideally, we would like to get back to traditional natural properties with circuit size. So something like CIKK, but without the need for membership queries. For some of the reasons I indicated, this seems like it could be tricky. But yeah, I mean, one of the really nice things about that work is that they're able to take the general framework of natural properties implies learning and apply it to a known circuit lower bound, known natural circuit lower bound for AC0 with mod P gates. And thus, they get a concrete, unconditional learning algorithm for that circuit class. Learning algorithms obviously are a desirable ultimate goal, but I think it's kind of a clear disadvantage of our move to Kolmogorov complexity that things no longer fit so readily into the world of known circuit lower bounds. So yeah, I would just leave that as an open problem. Whether anything can be done seems a bit unclear, but I think it could definitely be worth looking into. Thanks.
Any questions? How large is the threshold that you need to use in case of swift to get the learning result?
The threshold, like, do you mean the amount of error we could tolerate in the approximation algorithm?
I'm just curious if you only want to learn the uniform distribution, I guess you could put it into the epsilon.
Yeah, definitely.
But you have this extra randomness, this trick. Does it shift the required threshold to very close to n?
Oh, no, I don't think it does. No, I think the randomness gets subtracted out, and it would be still small.
Related to your last open question, do you have an idea for what maybe a variant of KT might be to kind of capture some restricted class of functions that we might be interested in learning?
Yeah. There is one version that I'm aware of from a paper of Allender et al. I think they call it KF there. So it's kind of polynomially related to NC1, using like alternating Turing machines and that kind of thing.
Thanks.
Thanks.